Good morning, everybody. This is G. Narsimlu, Associate Professor, Department of EC, St. Peter's Engineering College. Today, we are going to discuss about transistor biasing. First, let us know what is the meaning of biasing. Biasing is nothing but applying external DC voltage with proper polarity and magnitude to work two junctions of transistor in appropriate manner. That is called a biasing. The biasing only is effect over the junctions conductions ability. Generally, transistor having two junctions. One is collector to base junction, another one is emitter to base junction. We have to be applied the external DC supply, external voltages with proper polarity and magnitude to make it to conduct a transistor or to make it to operate a transistor in one among the three regions by affecting the junctions of transistor. Those three regions are cutoff region, active region, saturation region. When do you say the BJT now it is working in cutoff region? Means when emitter base junction and collector base junction, both junctions are in reversed bias, then you can say now transistor is in cutoff region. If suppose emitter base junction is forward biased, collector base junction is reversed bias, then you can say transistor is in active region of operation. And if suppose if emitter base junction is forward bias and collector base junction is also forward bias, then you can say now your BJT is working under the region of saturation. How do you make this? Emitter base junction forward bias or reverse bias, collector base junction forward bias, reverse bias, it's depends on the biasing mechanism. So without biasing, you cannot use solely one individual transistor for any applications. So the applying the external voltages, that is called the biasing, to make the to make the transistor work into the particular region of operation. Let me consider fixed biasing. In this fixed biasing, we have to understand you see RB is connected to the base terminal and RC is connected to the collector terminal. We have the AC input signal. Here C1 is the blocking capacitor. What it blocks? DC it can blocks. Okay, next you have to understand for the DC biasing mechanism, just you have to be omit this AC input signal. So this will be circuit converted as a DC biasing circuit. Okay, it means the base input you are taking from the DC only. Where it is DC? From here. This is a VCC was there. This VCC is nothing but it is a DC power supply. Okay, when you want to observe that DC biasing, you have to be open the input for the AC, so that when there is no AC input is impacting over the conduction of the transistor, only it is impacted by the only DC voltage which is drawing from the place VCC. That is the intention. Then you could understand the current passing through the base terminal is IB. IB which is coming from, actually it is plus VCC. Here one more current which is coming from the plus VCC is IC. You should be understand, you can have the current from the plus VCC like IB plus IC, something like that. Then you have to apply the Kirchhoff voltage law to the base circuit. What is the base circuit? This one is the base circuit. This one is the base circuit. What is this one? This one is the collector circuit. Okay. Now we are taking only base circuit. Just we have taken the plus VCC and RB to the base. That is called the base circuit. We are applying the Kirchhoff voltage law. Do you know that one, Kirchhoff voltage law? Okay. Sum of the voltages of all the loop is equal to 0. Then you can understand plus VCC minus IBRB minus VBE. It is equal to 0 according to the Kirchhoff voltage law. Then we can solve this equation to determine what is the IB. It is what is the amount of base current is entering into the base terminal of CE configuration. Then IB is equal to VCC minus VBE divided by RB. This equation derived from this equation. Okay. Next, let us look into that one. Collector circuit of the fixed bias circuit. For what is the collector circuit I stated, collector circuit is this one. This one is the collector circuit. Okay. Then same thing here. Here you should understand plus VCC. Here having IC is collector current entering into the collector, and this one is the collector resistance. It is a VCE from collector to emitter. Okay. Emitter was grounded because it is a common emitter configuration. Again apply the Kirchhoff voltage law. So VCC minus ICRC minus VCE is equal to 0. Then what is the VCE collector to emitter voltage? Means VCC minus ICRC. This one is the formula. The magnitude of the collector current is given by IC equal to beta IB. The relation of the collector current and base current when you are using in the common emitter configuration, because in the common emitter configuration output current is the collector current, input current is the base current. What is the amplification factor for the current? Okay, IC divided by IB. So what is the IB? What IC divided by IB is equal to the beta, that is the current amplification factor of the CE configuration. Then what is the IC? IC is equal to beta into IB. And from equation 2 we can have this one. IC is equal to VCC minus VCE divided by RC. You can also write like this. By using this equation, VCC, okay, minus VCE divided by RC. Okay. Then VC you can also write like VC minus VE. VB you can also write like VB minus VE. In the circuit, VE is equal to 0. Why? Because VE is connected to the ground, because it is a common emitter configuration. So again you rewrite VBE is equal to VB minus VE. VE is going to be equal to 0. So it is almost equal to VB. VC is also VC. Then we have to know about the load line and quiescent point. A load line which is going to be draw the line between the VCE and IC. It means that VCE is nothing but output voltage and IC is nothing but collector current. We have to be draw the line between the VC and IC while keeping the base current is constant. That is a line, you can be call it as a load line. That line you can be call it as a load line or a DC load line. Okay. Then how do you say IB is constant? Means you are applying the DC input for the base to emitter terminal. That you should be remember. That is also DC. Because if you're not applying the DC, that IB is also going to be changed. But you are applying the DC so that you can have the base current is constant. It may be 0 milliamps, 1 milliamp, 2 milliamp, 3 milliamp or 4 milliamp, something like that. Then you can write this one. IC is equal to VCC minus VCE divided by RC according to the previous formula, equation 4. You can see this one. IC is equal to VCC minus VCE by RC. Okay, You can also write this one like VCC by RC minus 1 by RC into VCG. Then you can rearrange this equation. You can write minus 1 by RC VCE plus VCC by RC. Now by comparing this equation with equation of straight line according to mathematical, y is equal to mxc, where m is the slope of the line, where m is the slope of the line. You should be understand what is the m here. M is nothing but minus 1 by RC, minus 1 by RC. Okay, when VCE is equal to VCC, when VCE is equal to VCC means what? Collector to emitter voltage is equal to the DC power supply, means there is no IC. Just you have to be understand. If there is no IC, then only you can be say that one VC is equal to VCC. According to the equation 4, you could understand. If there is no IC, then you can be understand. If suppose there is no IC, then what happened? VCE is equal to VCC. It means there is no conduction of transistor. Okay, right? Uh, and we get a point A. Okay, and we get a point A. Where is the point A? This one. At this point, you should be understand this is a point A, which is corresponding to the VCE is equal VCC. There you could not be expect any collector current because transistor in cutoff region operation. When VCE is equal to 0, when VC is equal to 0, IC is equal to VCC by RC. Very simple, you can be understand. When VCE is equal to 0, what is this one? When VC is equal to 0 from equation 4, what is the remaining term? VCC divided by RC. You see. This point you will get at point B. You can be understand this one. Okay. VC is equal to 0. Where the VC, this one, it is order of increasing the VC. This is the order of decreasing the VC. So there is a point you can have, see, VC is equal to 0, but at that point you can have this current passing through the transistor IC. It is equal to VCC by RC. Okay, when you draw the line between the A and B, between the A and B, then you can be say that one, that is a DC load line. DC load line. And you could understand the intersections points. You can be understand here intersection point P, intersection point Q, intersection point R, which are intersected with the base currents, base current curves. Okay, base current curves. You should be understand here. Okay, base current curves. These PQR, the points which are going to be present over the DC load line corresponding to the intersecting points with the DC load line and IB. Okay, these points are going to be decide that one whether our transistor is it now working in the cutoff region and active region or saturation region. Okay, applying Kirchhoff voltage law to the base circuit. You know this one, Kirchhoff voltage law, when you apply to the base circuit, VCC minus IB or B VBA. This formula already we have written here. IB or B is equal to VCC minus VBE. Just to move this one, VCC and minus VBE. And then what is this? IB is equal to VCC minus VBE divided by RE. The intersection of the curves of different values of the IB, the DC load line gives different operating points. It means that it depends upon the IB, intersecting point is going to be changing. Intersecting point, if suppose it is at center, that operating in one area, one region. If I intersecting point by making the IB is intersecting at another point, it is going to be working with another region, something like that. It means that setting the IB current by applying the DC voltage at the base to emitter terminal of the transistor will make you understand that when the transistor is working in the cutoff region or saturation region or active region. Okay, now let us consider this one. You see, you are having this one. Okay, selection of the operating point. When you select the operating point P, what happens? When you select the operating point P, what happens? Very simple. This one is the current, IB current. Okay, right? What is this one? Collector current. What is this one? Collector to emitter voltage. These are the points you should be remember. Collector to emitter voltage. Very simply, when you have this one base current which is going to be intersecting at point P over the DC load line, yeah, the collector current is going to be clipped off at the positive peak, and collector to emitter voltage is going to be clipped off at the negative region. This is a possibility is there. Okay, for the next point, when you have this one, choosing the intersecting point of the base current with the DC load line at R, mean then what happened? This one is, you can be understand, this is uh, IB current, but it can have the some clip of the IC and some clip of the VCE. Okay, this is going to be happening. Let me consider when you opting that intersecting point Q. When you opting that one intersecting point Q, it means that then you can have this. There is no distortion of the collector current. There is no distortion of the output voltage, that is a VCE. Means what? How do you select that one intersecting point PQR? These intersecting points, in the sense, these are the intersecting points due to the intersection of the base current with the DC load line. Intersection of the base current with DC load line mean who is going to be fixing that base current? You are going to be fixing that base current, because according to your applied voltage at the base to emitter terminal, so that you are going to be fixing that one base current. Okay, that base current is going to be intersecting with the DC load line. Okay, it may be at point P, it may be point Q, it may be point R. If you are able to apply the proper voltage with the proper polarity and proper magnitude, the IB, the base current curve, if it is intersect with Q point over the DC load line, then you can say that one, now our transistor is, now it is acting in the cutoff, sorry, in active region. Okay, next you have to understand what is VCE saturation, VB saturation, VB active, VBA cut in, VB cut off, all these things. Let us have the small discussion over this. Okay, by using a small table, we have the two types of transistors, like you can be construct by using silicon and germanium. Just you go through this one, 0.2 volts for VCE saturation. For silicon it is a 0.1, something like that. And you should be understand the quiescent point is affected. The quiescent point is going to be affected. It means that once you fix that one by applying the appropriate polarity, appropriate magnitude of voltage to make that one, the IB need to be intersect with the DC load line at the Q point only to make it to work your transistor into the active region. But that Q point is not going to be that intersection point of the IB with the DC load line not going to be maintained at the Q point only. That is a problem. What is the reasons are there? Because of what are the reasons? It means the reasons are temperature. The reasons are transistor current gain. This temperature, transistor current gain, which are going to be impacting over the quiescent point movement. That intersecting point maybe moves towards the P, the maybe moves to the Q. Then when it is moves towards the Q and when moves towards the R, then what happens? Some distortion will be takes place at output. Do you know the relation? Here you can be say ICEO, collector to emitter leakage current. Collector to emitter, when the base terminal is open, the collector to emitter, that is having the relation, it is equal to the 1 plus beta ICBO. ICBO doubles for every 10 degrees Celsius rise in temperature. Increase in ICEO in turn increase the collector current. Here we have the ICEO, it is defines the collector current. ICBO, it is going to be increase, doubles for every 10 degrees Celsius. It is in turn decide that one ICEO. ICEO in turn it is going to be decide that one what is the IC. Okay, IC is going to be variate. The increase in IC further rises the temperature at the collector junction, and the same cycle repeats. that excessive increase in IC shift the operating point into the saturation region, changing the operating condition set by the biasing circuit. It means that this IC is going to be changed. When IC is going to be changed, then what happen? We cannot be understand that one where you can intersect the IB over the DC load line. It means that shifting of the DC load line will be takes place. By that you can have this one Q point is not going to be maintained the same location, so that we can have the some distortions at the output because of the temperature. And one more point is that transistor current gain. Okay, this is also going to be impact, that you can be write like HFE, or you can be write like a beta is equal to IC divided by IB, because as you say that one a transistor current gain, if it is it deviates, then what happens? It is simply you can be say IC is equal to beta IB. I said you know that one. IC is equal to beta IB. When beta is changed, then obviously IC is going to be changed. That is advantages of the fixed biasing circuit. It is very simple, and we can be designed very simple, having only one component orbit. You can be connect between the collector and base terminal, but operating point can be fixed anyway in the active region of the characteristics of by simply changing the value of orbit. Thus it provides maximum flexibility in the design. The disadvantage is that thermal stability, because here ICBO is going to be impacted due to the variation of the temperature. It is doubles for every degrees 10 degrees Celsius. It is in turn it is effect over the ICO in turn it is going to be effect over the IC, and when rises IC, then it is impact over the temperature increment, and finally it is going to be burn out our transistor. This you can be call it as the thermal runaway. And you can also say that one, since IC is equal to beta IB is already fixed, but IC depends on the beta, which changes on unit to unit and shift the operating point. The stabilization of operating point is very poor in the fixed bias circuit, so that we have to be go with the another alternate circuit. Okay, another alternate biasing mechanism. This is the class for biasing of the transistor. In next class we are going to be cover another topic corresponding to the biasing of the BJT. Thank you everyone.